Hi everyone, it's Rajiv Ramchand here. This is session 7. We are going to be talking about risk. So let's get right into it. So right now, with respect to COVID, I think we're at a point that we're starting to ask questions like, who is likely to become infected? We know that some people are infected, some people aren't. So who are those people who are most likely to acquire the infection? We really want to know who is likely to become ill if they are infected with the virus. And then sadly, we also want to know who are the people who are at greatest risk or who is likely to die if they get ill from COVID-19. What we're in trying to answer these questions, we have to come up with some informed hypotheses about the people or the conditions that we think are at greatest risk, the exposures that we think might put people at heightened risk for infection or any of these outcomes that we're interested in. We come up with these hypotheses based on past research, descriptive epidemiology, what we've seen in the other sessions, and then talking to experts. You know, coronavirus, COVID-19 is one of a coronavirus, and we know that these viruses are around. So we know actually a lot about them and can make some really informed hypotheses about the exposures that we're most interested in. And then we have to test the hypotheses. And in sessions 8 and 9, I'm going to go through how we collect some of the data to test these hypotheses in a really sophisticated and analytic way. But before I do that, there's a concept that I just want to introduce with you, and that's the concept of risk. So in epidemiology, we talk about risk as the probability of an event during a specified time period. Some people quibble with this definition, but this is just a basic definition of risk. And I think that's, for our purposes, it's a pretty useful one. So if this sounds familiar, like, haven't we heard about risk before? Indeed, we have. When in session 2, we went over incidence and prevalence. Incidence is a measure of risk. Remember, we talked about incidence as the number of new infections over a period of time. And remember that we have, in this example of 5 people, 3 of whom got the infection, our cumulative incidence was 0.6 cases per week, and our incident density rate was 0.14 cases per person day. We went over what those mean. So those are good measures of risk that we can use then, and that we want to know, well, what are the things, what was so common about these 3 individuals? What exposures increased their risk for developing the disease? A lot of what we do in epidemiology comes from these 2x2 contingency tables. And this is just very basic, and down the road we can get a little bit more sophisticated. But for now, I think it's really just important to know, to look through this 2x2 table, what we call a contingency table. And you'll see that on our left-hand side, we'll classify people as either having the exposure that we hypothesized, or they did not have the exposure, and then they had the disease, or they didn't have the disease. And so we have a 4x4 table. And we can then estimate the risk of disease among those exposed, which is just those with the disease over the entire population that was exposed. And similarly, our risk of disease among those unexposed, which is those with the disease among all of those unexposed. And so we have 2 risk estimates of the disease among those exposed and those unexposed. What we then want to do is actually take the fraction of these fractions, if you will, and we can estimate the relative risk. And that helps us answer the question, does the risk of developing the disease differ between those who are unexposed and exposed? And so the relative risk is just the risk in the exposed over the risk in the unexposed. And so you have, again, A over A plus B, exposed with the disease over all those exposed, over C, those with the disease who are unexposed, over C plus D. And this is a fraction, so it's not going to be a negative number. If it's greater than 1, we have an indication that the exposure increased risk. If it's equal to 1, that means there's no difference in risk between the groups, so there's no influence in exposure. And if it's less than 1, we actually see what we would call a protective effect, that those people who are exposed have lower risk of developing the disease. So let's just take an example, and this is a very basic one. Does high cholesterol increase risk for coronary heart disease? Now, this is actual data from something called the Framingham study. It was a long cohort study, and you'll see that they have coronary heart disease, or not coronary heart disease, and then high cholesterol and low cholesterol. And I just walk through this example here that you have those with high cholesterol and the disease over all of those with high cholesterol versus those with low cholesterol and the disease over those with low cholesterol. And you just work out the math and you have an estimate of 2.7. This study was restricted to men. So what we can conclude here is that men with high cholesterol have 2.7 times the risk of developing coronary heart disease relative to men with low cholesterol. A very simple estimate. Now, it gets a little bit more complicated. And one of our biggest complicating factors is something we call confounding. And a confounder influences both the disease, high cholesterol, and the outcome, coronary heart disease. And because it exists there, it kind of distorts the observed disease exposure relationship. So smoking, if we can conclude smoking causes both, then is this relationship, is the direct pathway between cholesterol and heart disease, is it independent of smoking, or does smoking somehow influence both of these? And if we can adjust for it or control for a person's smoking status, then this relationship between high cholesterol and exposure would go away. We're going to see a lot of that. There's a lot of ways in advanced epidemiology that we can adjust for this effect of smoking. But it's just something to keep in mind that when we see these relationships, that there may be some multiple other things happening in the background. And we just really want to be sure that we avoid kind of causal language and really think through the potential confounding relationship. There's another important factor to consider, which is effect modification. And a modifier is something that changes the relationship between the exposure and disease. So here we have cholesterol and heart disease. And let's just take gender, for example. I showed the relationship between men. What if we had a group of women in there and the relationship between cholesterol and heart disease was different for women than it was for men? Either it didn't exist or the magnitude of the effect was greater or less. So that the risk was much more elevated for women, or had a lower, the risk was much lower for women than it was for men. So these are, again, things that we really want to be careful and think through when we're thinking about these 2x2 tables and the relationship between exposures and disease outcomes. I'm really not going to go into this a whole heck of a lot, but there's more that we can do with these 2x2 contingency tables than just estimate the relative risk, though what we'll be seeing, I think, in days to come is more the relative risk. So two examples are we can calculate the attributable risk, which is how much would risk be reduced if exposure was eliminated, and then population attributable risk, which is what proportion of disease in the population can be attributed to the exposure. And in these instances, we are really interested in the difference. So we take the risk in those who are exposed, A over A plus B, and we subtract from it the risk of those unexposed. Now, answering this question actually requires some really strong assumptions, but if you are confident in those assumptions that our relationship between exposure and disease is actually causal, and we're not as concerned about these confounding influences, we can construct this estimate, and I'll show you an example in a second. The population attributable risk looks at all of those with disease in the entire population, and from it, you subtract the risk in the unexposed. So looking back at that coronary heart disease and cholesterol, our attributable risk is 0.06, which we could then conclude, if we believe strongly, that among men with high cholesterol, the risk of coronary heart disease could be reduced by 6% if they had low cholesterol. Notice we use that language carefully. If they had low cholesterol, we're not talking about reducing cholesterol, although one could potentially make that jump to that kind of public health action. For our population attributable risk, our estimate is 0.03. And we can then say that 3% of coronary heart disease in this population is attributed to high cholesterol. Now, the problem is that we can construct these population attributable risk for multiple exposures, and they might not ultimately equal 100%. And that's because a lot of our exposures are not mutually exclusive. So if we were to think about obesity, smoking, and coronary heart disease, for example, we know there's overlap there, and that will influence whether we could, ultimately reach, we're not achieving, necessarily, we're not striving for 100% in constructing these estimates, but they're still pretty helpful. So that's it for this session. I hope it was helpful. Next session, we're going to be talking about how we start collecting the data. And there's 2 more sessions. So how we collect the data prospectively, and then how we collect the data retrospectively. Until then, be safe, be healthy, and stay informed. Thanks.